So I want to eventually I want to explain the plan of this talk will be the following. So first, well, at some point I'm going to prove the theorem that I stated last time. So we have delta scheme, and then so the claim is that the canonical map that extends to so what it means, what it says is that first of all, there is some stack shared prismatization mark, which lives over ZP prism, and its pullback to shared prismatization is this one, and it also receives a map from X times ZP prism. So we have a map like this, such that its pullback prismatization is so I'm going to explain a proof of this. That will be hopefully the first half of this talk. And then I will explain the notion of flatness for in scheme. And as an application, we will study, this will be an input to the study of the kernel of this map in the case when X is the multiplicative. You'll see that in particular that this kernel is Cartesian to something, to smooth affine groups. So, all right. Well, first, so I want to prove this, and so let's start. So, beginning of the proof. Namely, I want to explain construction of X shared prism question. So I will define it just a pointer of points. So suppose I have some angular input. I want to tell you what the points. Well, first of all, this stack is over the prismatization. So it means that one piece of data is just a point of ZP shared Cartesian. Okay, so and another piece of data is a point of the following fiber product. So you take X and you look at W mod C, the font. Well, so this is the ring stack associated to this Cartesian divisor, and now you take the fiber product over X of Q mod C of R. And the fiber product, well, with perfection of Q mod C of R. So here X per by definition is inversely limited with respect to Frobenius on X inversely limited function. Okay, so so the maps here in this fiber product I believe this the most obvious. So you have a map from here to X. This is a map from X here, and this map is just given by map from W to Q. So to make sense, so I need to do two things. So first of all, I have to explain. I have to construct this arrow. They also need to explain why, if I take this shared prismatization with question mark and pull it back to ZP shared prismatized, then I get a stack. So this requires some preparation, which I believe it's useful on its own ground. Well, apparently it's maybe. Well, tell me if it's everything I'm going to say is well known. So it was kind of substance new to me. So what I want to do, I want to so this will be iteration. So I want to describe in a very general setting mapping spaces between animated objects. So description of certain mapping spaces. Spaces between certain animated objects. So, well, in general, taking spaces form a groupoid, maybe in an infinity groupoid, but in some cases, this groupoid is actually a set. And I'm going to describe a very general, well, which is some situation where it is a set. So, and this is useful for proving what I want here, and also for describing, say, prismatization and shared prismatization of perfectoids and semi-perfectoids. So the setup is the following. So I will start with well, the first part will be there will be no animated algebras, just a warm-up. So this probably goes. And at least, so let's consider. Suppose I have a perfect FP object. And I'm interested in mass algebra homomorphism to some algebra B. And all I'm going to assume here is that B is equal. Well, then so if I have such a homomorphism, I can reduce it mod B, and because R is perfect, W of R mod B is just R. So I get this. And the claim is that this map is in iso. And second, I can consider replace B mod P by B flat, which is just inverse limit with respect to Frobenius. So the map from B flat to B mod B gives me this map, and this is also it.
Am I right that the second part is obvious?
Is obvious.
Because R is perfect. So of course it's
Exactly.
now another question is when you write B mod P, is it do you mean
Just
the naive? Naive. Probably doesn't matter here, but anyway, it's naive.
Right. So okay, so maybe I will know if I should. I can give a formula for this map. So suppose I have F that goes. So I need to show that this arrow is an isomorphism, and I just want to construct the map into inverse. Suppose I have an algebraic isomorphism from R to B. And I want to produce for you. I want to lift it to a map from W of R to B. So what we want is a map from W of R to okay. So suppose let's say this is FT. Suppose I have a retractor, which is I. So what can I do? So the idea is to consider the weight polynomial. So I take A0. I extract root of it. I apply F to it. So this is an element in B mod B. Now I can lift it in any arbitrary to B, and then I can take its into that, and then I can add to it E plus F A1 into the minus n. Again, I need to lift it, and minus first power. So this is a Reed polynomial, but except that it's applied not to bit vector A0, A1, and so on, but it's Frobenius. Okay, and so this depends on n, but I claim that the limit as n goes to infinity is well defined. It exists and doesn't depend on choices. In fact, that's easy computation. If you have two elements which are congruent mod p, then the p to the f power are congruent. So that's the form. Now I want to generalize this. Are there any questions? So generalization will be the following. Suppose I have make the same assumptions on R is perfect. But B is enclosed by any P-complete matrix. And the map is mapping space. This is morphism is in animated objects. So in principle, in general, this form is a topological space. It's infinity group. But the claim is that in this situation, it's
just an algebra means ring. If it's
yeah,
algebra,
ring,
not
ring,
algebra.
ring. So the claim is that this is the same as it's a set. So it's the same as maps and FP arguments from R to B flat. And B flat here, by definition, is well, you take pi 0 B. That's an ordinary ring. You reduce it mod P and take the limit vector. Yes. So so this is the generalization example A. And the proof
And R is a perfect FP algebra. And there is no animation because perfectness doesn't allow interesting.
So in particular, this topological space is in fact discrete. This is useful. And the proof is so proof the key observation, the key fact is that if I consider the cotangent complex of W of R integers, CP, and take its P completion, that is zero. That is because the cotangent complex of R over FP is zero. That's the main observation. And this implies that the canonical map, so I can consider W of R, I can consider E, and I can look at its Voisnikov truncation. So there is a map from this form from W of R out and -1. And this map is in it. So that's an application of deformation theory. So think of this as a square zero extension of this algebra. And so deformation theory says that if the cotangent complex is zero, then for any such map, there is only one way to extend it to a square zero extension. Okay. So and then you do so that the are there any questions? So here is an application. Suppose I have a Cartesian device. So it's a point of R prime, some unipotent ring. Then, we can compute home from W of R. Again, R is perfect. To one truncated animated. namely, I take W, divided by C, and take R. So this is just a P.
So R prime is what kind of object?
Just P-nilpotent ring.
P-nilpotent ring, and R is a perfect P algebra.
All right. So okay. So I claim that this is the same as well. There will be several. So first of all, this is home. Again, the claim is that it's discrete. One way of describing this is well, you take R prime and you take flat. So you take R prime mod P and you take its limit perfection. Another presentation of this is it's just home to R prime. And finally, this can be also written as home from W of R to W index. Pointer.
So this in the second, is it the delta?
It doesn't matter. In fact, it's a consequence of this fact. Any map from W of R, where R is perfect, to any delta ring is automatically delta. So what is behind this statement? I need to prove that's this observation. So the key is the following: if we take pi 0 of W and take its flat, take the flat construction. So then this is R. Well, this is GA flat. So I think of this as a functor from P-nilpotent rings to Cartesian P rings, and that's okay. So well, I can prove it, or I can leave it as an exercise. So this is.
But will you prove it in your notes?
I can prove it in my note. Yeah. Okay. So I don't know. So so another way of phrasing this is that W of R, the prismatization of this of this formal affine periodic scheme is just a stuff W of R times CP. So why is that? Because so what is a point here? First of all, it's a point here plus so R prime point of this of the stack is a R prime point of ZP prism together with a map like this. But you look at the second isomorphism here. Well, it's the same as just homomorphisms. Well, R prime point of this photosphere. So, and similarly, W of R is both W of R. So, okay, here is another observation, general observation about animated algebras. So, okay. So, suppose we are in the following situation. So I have some algebras A and B, or rings. So this is the ring. And also I have I into A and J moving to B. These are quasi-ideals. Then, well, so in particular, this map makes B into an A algebra, and consequently, it makes this animated algebra into an A algebra. So I can consider morphisms formed. Now, in the category of animated A algebras. From one of I A model one of G. And again, the claim is that, so again, so consider not all maps like this, but only maps A algebra, right? So the A algebra structure here comes from that fixed map from A to B. The claim is that again, it's this. This is the set of all maps of quasi-ideal pairs. So you have A, you have, let's say, Z. Then you have one. I have so alpha is homomorphism of A. So in general, if you have two quasi-ideal pairs, then mapping space between these quasi-ideal pairs and this category of animated algebras is a groupoid. But the claim is that if you consider linear maps, then it's And I guess this is similar to the more basic property of just complexes of abelian groups. You consider maps between two complexes like this, such that the composition of a map from A to this cone. If you fix this map, then the fiber for given f is a set. It's precisely. So I want to use this. So here are some applications. So application. Well, maybe I'm not going to make any attempts to explain this statement, but maybe suppose I want to learn a proof. So what would be a best reference? It's probably it boils down like so you still need to know what a map of animal have. Oh.
Sorry, a reference for this fact?
Well, maybe for basic of animated objects, things.
Well, you are asking for a good reference.
Yes.
I can give a reference. Right. Namely, some time ago, I posted an e-print in which I think it's called the notion of ring groupoid, where I tried to explain everything about short. So let's call such. I tried to explain in elementary ways basic notions and facts about, so to say, short animated rings, namely those where the only pi I is 0 for I strictly greater than 1. And I tried to give references. So I tried to write everything as explicitly as possible. Now there is always a price for being explicit. So I'm not saying that this is the best approach, but anyway, I tried to write something, and also I gave reference to works, for instance, where there were previous works where non-commutative rings were considered in details, and the non-commutative story where everything is similar except that you cannot, strictly speaking, refer to this, and so on. So I wrote, how to state, the first topic on this subject. And of course, I'm not saying that this is the best, or even that it's a good.
All right, thank you. So I expect that a similar fact holds for holds when you replace when you have an animated and truncated animated ring, and A is n minus 1 truncation. So fix a map between n minus 1 truncation. So,
sorry, but is there a reference for this fact?
What?
Is there a reference for this fact in particular? There's a good reference for this fact. I mean, I would think about it as you would build this animated ring by starting with A and sort of maybe coning off a bunch of elements, so adding a bunch of one cells, forming a cone of a map from a polynomial ring into A, and then maybe adding some higher cells. I'm not sure I know of a good reference.
Probably if somebody wants to understand this, then a warm-up would be first to check the corresponding additive statements. So suppose that they're not rings at all, but just A and B. Suppose that A, B, I, J are just abelian groups. So we're talking, then the cones are just complexes, and we want to compute. And then what does home mean? Home means that you take home in terms of complexes and truncated, so you don't want to, you forget the positive degrees. And then instead of saying, you cannot say A algebra, but just means that you fix a homomorphism from A. Then you get a purely additive statement. And then this is a question about complexes, abelian groups, or abelian categories, and you can prove or disprove it by hands.
Correct. Oh, it's the additive statement. All right. So, so what are the applications? So, so again, I'm going to fix Sheared divisor. Right. And my A will be W of R, where R is and I will be actually an ideal. And I'm interested in maps from W of R model to images short algebra. So what we learn from by combining these two statements is that this is again a set. Namely, so the claim is that this is the set of, well, most naive set. So you look at quasi-ideal pairs, W of R, you have I, and you have W of R prime, and well, so C is a point here. So it's represented by invertible W of R module. So I will call it J. So locally, at least, you can think of this J as just W. Then this will be multiplication by X. J, if you. So a point of this step is an invertible W of R prime module together with a map to that. So and so the claim is that this mapping space is the set of commutative.
Yes. In other words, so we want to compute forms in animated rings, and instead, and the claim is that you can compute it in the most naive way. Each of the animated rings is represented by short DG ring. And you just take naive homomorphisms of these DG rings. I'm just retelling what you explained to me by.
So why is that? Well, we have a map. First of all, we have a map from W of R. So if I give you a map between animate rings like this, I can compose it with this map and get a map from W of R to this. We computed this map. We found that this is this set, right? So if you give me an element here, a homomorphism, I can take the composition with this map and get an element in this set. So this gives me this map. And now, so let's now fix this composition. So this is an element of this set. And then by this general remark C, so we are looking, so let's call this composition F. Then, so it's given by just by a map from W of R to W of R prime. And then by applying remark C, we see that the fiber is precisely given by this. Are there any questions? Okay. So what we so this is very useful. So what we derive from this is that well, literally it says that if you consider the prismatization of A is this, and look at the map, structure map. So on R points. So this is a groupoid and this is a groupoid, but the fibers of this map are sets. Well, there is a better way of phrasing this. So if you consider the prismatization, and if you fix a map from R prime here and take the fiber product, I see ism spare then this is a scheme. Well, this is actually an additional statement. I explained that from what I said, it follows that as the functor of points of this guy, of this fiber product, is actually a functor that takes values in sets, not in group points. But the claim is that it's represented. Am I right? I hope. Okay. Well, maybe
just one. So there is spec R or spec R prime. And
yeah. Okay.
Yes. I think there is a name for this situation. You say that people say that the morphism from instead of saying that such Cartesian products are schemes, you can say that the morphism from the prismatization, you can say that the right vertical arrow in the diagram is schematic. It precisely means that the fibers are schemes, and moreover, fiber here is understood in a slightly generalized sense, not necessarily fibers over naive points, but fibers over schematic reason.
Okay, so this fact has a direct analog, straightforward analog for the sheared prismatization. But this, literally, it's not true. You have to. It's not represented by scheme. It's represented by some. It's still a functor to sets, but it's not represented by normals. Okay. So this is one application, and another application more relevant to what I'm now referring to the proof so of the theorem, and the observation is that so another application. So let's try to understand this object. So to do this, I recall that pi 0 of Q mod C for any Cartesian divisor is GA bar. G bar is or bar is co-limit perfection of R. So now, so I claim that X perf of C is it's X perf of GA bar because this is already perfect, that's the same as X. And right. So why is that? Well, I will explain it in the case when X is affine. So in this case, this is a delta become.
Just what is obvious here and what is to be explained? So there is several.
Only first claim has to be explained.
Which one? So can you put an exclamation mark over this crucial?
Okay, so the map goes in this direction, and because there is a map from Q mod C to its pi 0, and the claim is that this is an isomorphism. But this is right. So why is that? So what is
just so. So you are saying that only the first equality has to be explained, and X-perf. So of course, X-perf comes from some delta scheme, but can we just forget about this and say that this is perfect?
Well, so I need to know something. So this is almost immediate consequence. I believe that. So what is X-perf by definition? Okay. So X-perf is spoke of or limit perfection of a yes. Well, I need to all my schemes are periodic formal schemes, so I need to take its P-condition. So what I get is a P-complete perfect delta ring. They believe that every P-complete perfect delta ring is isomorphic to W of R for some so this is a P-complete perfect delta ring.
Yes. Well, it's a perfect. So the important thing is that perfection here is in the sense of delta rings. So it's not, we do not live in characteristic P.
Yes. Okay, so with this observation, I believe this is a consequence. So what is the general recipe? So we're computing whole morphism from this from this object to Q mod C, and the observation is that so the general recipe is that I have to take pi 0 of this animated algebra, and I take its apply the flat function. So this is pi 0, and then I need to take flat on this. It doesn't change anything. All right. So
Sorry, I have a basic question about this middle part. We don't need to assume anything like J is injective into B for this middle chords to hold. Yeah. I have to assume don't think so.
Also, when J is very much non-objective. Multiplication by P or something on the rim vectors, right?
Yes, I see. Okay. Okay, sure. Thank you. Okay.
so let's record what we learned. So this is X of G A bar of R. Okay. So there are more questions on this. So now so now I have to explain two things. I have to explain why the pullback of this object to ZP shared is
So
maximum.
now we, so all this was long digression.
Long digression.
So maybe the last item was closer to the original thing, but now you are starting to prove the theorem. You already explained the construction, and now you want to check that the construction is doing the right thing. And what does it mean here? To do it right.
Okay, so first we need to check the following, that so we need to check that if C is well, it's strongly it's a point of sheared prismatization, but for simplicity of my notation, just assume that this is point. So I don't like walking.
Just a moment. C was in
it was a Cartesian device, right? But now what I'm going to check, I need to check that if I pull it back.
So do we have to check one thing or more or two? Let's say so
two. Well, so we need to check that. Yeah.
You don't have to formulate the second items to
yeah, I know.
right
I mean,
away, but
what I'm going to check is now that if I take maybe I will, right. So if I take this x shared question mark and I make base change, you see here there's no base over ZP. Then it's x. So explicitly, what I need to check is that I need to check that this x c so I fix this part of structure, but moreover, C is an element here. And I need to check that this is x which is recall what this is. So this was a so I'm going to use the construction with W check, but I want to rewrite. So this is x of W not C of R. Okay, so this is x of W of R. Then I take fiber product with x of cube of model C. And C now is C is how so C is well C must be here an element of W check, and so W check is I recall that W check is the fiber product of W Q curve and Q. And so if I have C of this form, then how it gives an element in W check? Well, you take C here and you take P. So this is actually P. And here you have Q1. So this is some groupoids, and you take the fiber product. This is again. That's this is equivalent to saying that we take x of W check mod C of okay. So now let's compare this to two formulas and observe that future of P. Well, this is a perfect delta ring. In particular, it has no P torsion. So this is a ring. This ring is G. Well, so we get the same answer. Well, it remains to check that to prove this assertion, it remains to check that some maps are the same, but I hope it's okay and easy. Right. So that's the argument for this one. So I explained why if C is a shared Cartesian divisor, then you get the same.
So you have checked the first. There were two
Yes,
things.
yes.
Check, and you have
Maybe I want to write a slogan here.
will this slogan correspond to
the
what
construction.
we have already checked, or to what we're going
To what you
check?
already checked, or just to the very construction.
The slogan regarding the construction.
So we have algebra few mod. This is an animated. Oh, sorry, few mods. And it's pi 0. So C here is any activity divisor, not necessarily a shear. Still, pi 0 of this is something. It's an algebraic characteristic P. Namely, this is GA or NX. There is a map. Well, because Q maps to W of J bar and well, Q mod C, because the first coordinate of C is the 0 coordinate is important. It means that this map descends the map from Q mod C to J. And this map is an isomorphism on pi 0. You can check it locally, and locally you can assume that C is so then it's
but this is not. Is this a slogan?
no, this is an observation.
This is an observation.
Observation. So a map, as prism. So just want to remark that pi 1, well, of this Q mod C, it also can be computed. It's something. It's J sharp mod J sharp hat, but it's not 0. That's important. The splitting G bar Q mod C depends on the shear of but W of J bar made into W of humans doesn't. That's that. So if I have a shearing it means that, well, essentially I'm in this situation. So what is a splitting? Well, this is an animated algebra. And it's, I explained to you what it's pi 0, right? So there is a map from Q mod C to its pi 0. And I'm asking for a section of this map. So, a section of this map, well, it did not exist in general, but locally, well, when you choose a sharing, it does exist. So one way of constructing this splitting is by observing that. So remark that if C is P in Q, then well, we can construct this sharing as follows. I consider this splitting as follows. This is Q perf not P, right? It's observed above, and this maps to. So this is a splitting. Is a splitting of the map from Q mod P to P. So more, there is an abstract, well, this is a very explicit construction of this splitting, but you can use another construction. Well, you can, there is a soft argument for the existence of the splitting in this case, namely, this is visibly an FP algebra, and its Y0 is perfect. There are no square zero extensions of perfect FP algebras, because the cotangent complex is zero. So shearing gives me a structure on FP algebra, and this gives me this. So this is an explicit way of producing this. So
I'm a little bit lost. So you made a claim that the splitting depends on shearing, but after you pass to W, it doesn't.
Yeah.
And why is this true?
well, because I can that's precisely that construction. So I can write it as W curve of W mod C, and then I can map it to W mod C. That's the construction. Am I right? Yeah. Okay, so this is a map of yeah. That's so this so I constructed for you a map from some bit vectors on Q mod C, and because by the universal property of W, it's a joint functor to forgetful functor from delta X. This gives me a map from W of G bar to W of Q mod C. So this is map. This is map of delta X. Okay, so I reduced for you this map, essentially by looking at that construction.
So who is the map of delta rings here?
Well, this is a map of So, uh, yeah, so maybe let me, so I suggest that I do the following. I take 2 minutes to explain this map, or this map. It will not be a complete argument. I will explain what.
Just so I want to understand where. So there were 2 items to check.
And I check one.
You checked the first one.
Yes.
Then you formulated and explained a slogan.
Yes.
And now
Now I want to explain, start a construction of this map. It will not be complete, but I will explain the details in notes. Okay.
Just one, but so first of all, what right now remains to
Okay, so let's see. Remains to construct this. So construction of well, so what I need to do, I need to produce a map. So I fix some point point of points, and I need to produce for you a map from Spark to this this fiber product. This fiber product. So first of all, I have a map from X to W of CL. So in fact, I have many maps. There is a map that I called W delta. Comes by so if X is spec A, then it comes from the map from A to W. And this gives me this map. I want to recompose this map with Frobenius on X. Now here, I have a map to X of GA bar. Spec. So what is this map? So this is X of G, right? So it comes from the map from you take GA, you map it to GA bar tautologically, and then you compose it with Frobenius on GA. That's the right, and this is recall that this is also X turf of this is the same as X turf of human. So I already produced a map to this product. So then there is a map to X mod C, and which is given by a map from W to R. Here. not sure that that's ambiguous notation because the input depends on our also, I don't know. This is not constant. It is not a ZP1. We need to take x times per car and then take. So okay, so I have I have this diagram, and the claim is that it's commutative. So once I have this claim, this gives me a map from x times this. Okay, this gives. So I want to stop now.
And in your notes,
I will explain the
more.
computation. Right.
Can I add also one more slogan?
Yes.
Right. There's that a lot of these so these statements for delta schemes, I mean, just as the prismatization depends on a ring stack, these prismatizations of delta schemes depends on the bit vectors as a delta ring stack. The bit vector is a delta ring as a delta ring, and they're given rings R and R prime. There are more maps of delta rings from W bar to W bar prime than there are maps of rings from R to R prime.
It's too long for a slogan. We need something like, at least I need something like make America great again or something like that. So can you write something on that? If it's a slogan, then
yeah, that's an example of the situation that
can you write the slogan on the page?
Okay, I can write something. So yeah, this is really just an addendum to the slogan. So so given rings are animated rings and B, there are more maps. Delta rings from W of A, W of B, and ring maps. So for these various constructions that apply to delta schemes, what's relevant is really delta maps from W of A to W of B. So I think another way, I mean, one way of phrasing this is that, so an example is that the map from GA bar to Q on C, so having such a map depends on a shearing.
May I ask a question? So you said that given the rings, there are more delta maps, and is it good or bad?
It's a good thing. It means
which is good. So and this is a part of the slogan.
Right.
So which is good?
Which is good, yes. But sorry, just as an example, the map from GA bar to Q mod C depends on this shearing. But W of GA bar to W Q mod C. And I think that's another way of, I mean, well, that's more or less, yeah, a restatement of why why one has this construction. And I think that there are also some other constructions, and maybe this is a bit of a digression, but there are some other constructions. Well, there's some construction with the drum stack and prismatization that work for delta schemes. Well, okay, so maybe I should just say briefly. So as an example of something else, one can prove with this. So if okay, so let's say X is a smooth delta scheme. then there's an equivalence. So let's do the Shiho between say it this way. So this is in the unshared setting. It's an equivalence between the deform stack of X, we know potent P modules, and the P deform stack. P deform stack of X, which is classifying modules with a locally nilpotent P connection. And I think this statement is also something that along these lines. So both of these are sort of parameterizing ring stacks over ZP, and they're not isomorphic. But when you apply bit vectors, they become isomorphic as delta stacks. That's sort of what.
What are the stacks in question?
So the stacks, right? Sorry. So the stacks are. So in this case, you have the map GA sharp to GA. Just the inclusion. This is the ring stack that gives you the deform stack, and then this P deform stack comes from the ring stack GA sharp multiplication by P to GA. So these both give you ring stacks over scope CP, which are not isomorphic. One is an one is an FP algebra stack and one is not, but they become isomorphic. So these two ring stacks become isomorphic after you apply bit vectors. They become isomorphic as delta roots, and right, so that also leads to this equivalence. Okay, sorry, maybe this is a bit of a digression.
Yes. We have a break now.
Okay, so maybe we'll sort of start something a little different now. Maybe I can, since there's not so much time today, maybe I can at least start with explaining some of the motivation. So essentially, Benjamin and I wanted to explain some notion of flatness that we're starting to think about. But maybe first I should explain what we want to do with it. Okay, so right, so the goal or a goal is to the goal is to describe quasi-co of X sheared prism in at least some cases. Okay, so actually, well, there's already the base, sort of the absolute case where X is above CP. But I want to start, what I want to discuss now is sort of the relative case. So specific example, so that's maybe more variance. So explicitly, let's consider the following. So I'm now going to take P to be greater than 2. And then we've seen that there's a map from scuff of ZP double brackets Q minus 1 to ZP sheared prism. And this I'll call rho Q deform. This is this Q deform point. And it's a variant of the Q deform point that exists in the prismatic theory. So explicitly this classifies a strongly primitive element, namely it's brackets Q to the minus P minus 1 over 2 times the brackets Q analog of. So this brackets Q analog of P is sort of the usual Q deform point in the prismatic theory. And there's a slight scaling factor by a unit that you add in this sheared business to make it strongly primitive. So I think we explained in our sketch that this is actually a strongly primitive element. But in particular, this gives a map from here into ZP sheared prism such that when you set Q equals 1, it becomes the de Rham point. So this is this Q de Rham point. So we can consider. So well, I'm going to write this as X Q de Rham hat, and by definition, that will be the pullback of the sheared prismatization along this point. So our goal is to just write this, and in particular, this construction. It's giving you some sort of deformation. Well, again, when you set Q equals 1, you get the sheared de Rham stack. So you get some sort of deformation of the of the sheared de Rham stack. And so here, maybe the basic example to start with is X being the multiplicative group. And in this case, so one of the benefits of the multiplicative of GM is that it's a delta scheme. It's a delta group scheme. So since GM is a delta group scheme, well, we get a map okay, so we get a map from GM cross cusp of ZP double brackets Q minus 1 to GM sheared Q de Rham. So you get a map like this. So when Q equals 1, this map does not depend on the delta structure. So when Q equals 1, this is the map from GM to the sheared de Rham stack that you have for any X. Okay, so when Q equals 1, this reduces to the map X to X from for any X. If we want to construct this map, we need to use a delta structure. But okay, so in fact, not only is this a map of stacks, but it's a map of group stacks. So
it's kind of epimorphism.
yes, so this map, let's call it star. Is an epimorphism. And here, when I say epimorphism, I mean epimorphism in the category of sheaves for the flat topology, and it's an epimorphism of group stacks. So this is, well, this follows, in fact, from the result for the unsheared de Rham stack, which is in the paper by Volodya on the one-dimensional formal group over ZP. So this is really yeah. So this is sort of a sheared version of constructions.
So you can explain the construction of star when P is greater than 2, but using the theorem that we discussed earlier. So
Yes.
it's also works also for
Right. Sorry. Thanks. That's a great point. So if we use for P equals 2, so for P equals 2, I think we don't have X. So one comment is that when P is equal to 2, we don't have X sheared Q de Rham for any X, but we have it for a delta scheme using the construction that Vadim explained, and then you have this map as well. Okay, so it's an epimorphism. So
again, so if P equals 2, then we don't have row Q de Rham, but can you say again what do we get in this case?
So a remark. Right. So a remark when P equals 2, we don't have X sheared for any x, because we don't have a map from this map rho theorem from stuff of ZP double brackets Q minus 1 to ZP. I think, in fact, okay, so there's always a map to ZP prism, and I think we checked that it doesn't lift to ZP sheared prism when P is equal to 2. So we don't have this map. We have this map if you add a square root of Q. We don't have this map itself. But we do have it. For x of delta scheme. Because for x, when x is a delta scheme, the shear prismatization of x descends to the prismatization of CP. So we do have it for x a delta scheme, because then we could define, I don't know, put this in quotes or question mark, x q derom sheared question mark, and this is defined as a map as the fiber product spuff of ZP double brackets Q minus 1, fiber product ZP prism, no shearing, with X sheared prism question mark. And this is the Q derom point, which is given, well, which is well defined to ZP prism for any P. So unsheared. Okay, so the first comment, right? So the first comment is that this map is an epimorphism of group schemes. So we can, oh sorry, it's an epimorphism of group stacks. So we can describe, right? And so actually, so far I don't need to be working over the Q line. This would be true over ZP sheared prism, or ZP prism for that matter. But I wanted to specialize in this case. Okay, so we can write, so GM sheared Q derom as the quotient of GM over the Q line. Modulo some group, I'm not sure exactly what I should call it, let me just call it G, where G is the kernel. So very explicitly, we can, if we unwind the definition of the sheared prismatization, we can, so G is the sheared analog of the group in the one-dimensional formal group paper. So G is defined by the following formula. It's defined as pairs. So let's say G of R is going to be pairs. X belongs to R cross. Y belongs to W of R, such that, well, first, brackets x to the p minus 1 equals this quantity that I wrote up there. So that's brackets q minus p minus 1 over 2 times q analog of brackets p times y. And so this would be as in the unsheared setting. This would be as in the unsheared setting with an extra p power, but also with the condition that brackets x minus 1 minus b hat of y is null. So you have this map here, which is a surjection. And if you use one of the quasi-ideal models for so how do we describe the kernel? Well, we think of this as being given as the units in an animated ring given by a quasi-ideal. So the kernel of this map is basically a fiber product to give an element here such that the image in the ring is lifted to the quasi-ideal. That gives you this formula.
And so here you are using the model from Vadim's October, which was one of the models explained by you in talks.
Okay, so this is the description so far, and okay, so in particular, a consequence of this is that we can think of what is a quasi-coherent sheaf over here.
So anyway, so it's a group in scheme.
It's a group in scheme. So this is G is a group in scheme. And okay, so I said this particularly over the Q-Derome point, but yeah, maybe I should have said that this is a group in scheme that lives over, that in fact is defined over, well, in fact, over ZP prism. So maybe I just add this as a remark. So remark, actually, yeah, sorry, I should say this. So this is the group in scheme. Group in scheme is defined, in fact, it's defined over ZP prism via the above formula, via the kernel of the map GM cross ZP prism to GM shear prism. So actually,
Yeah. So you are saying that this group scheme it's defined explicitly here over formal disk. This formal disk maps to the prismatization of CP, and in fact, science tells us that this scheme canonically descends.
yes.
It's this. So and this follows from the theorem formulated by Vadim beginning, but now is the answer as explicit as this? So in other
No.
words, suppose I take any, what does explicit mean? So probably it means that you take any C in, which is a primitive good vector, but not necessarily a strictly primitive, and then you would like to write some kind of explicit condition. And there are some doubts because there was some derived stuff. There was some sign talks today. And here we want to have an explicit answer without any animated.
Well, I think, sorry, if you have a strongly primitive element, then you would replace this quantity by that strongly primitive element.
Yes.
And
this is clear. But if it's not strongly primitive, then yes, of course, you have a recipe, you have to first make some choices. But others, if it's an in scheme, then it's a direct union of subschemes, which are maybe one thing is this in scheme it's a sub in scheme of something explicit.
Mm-hmm.
So you say that it descends to ZP prism. Is the answer also a subgroup of something explicit? Is it does this in scheme live as a sub in scheme of something simple, or maybe it just maps non-injectively to something simple?
so I didn't, okay, I don't know the answer right now. I think
not immediately.
Yeah, I can try to say something more with a bit of fun. Yeah, okay. So, sorry, so maybe I should have said this first, but so if we say that, then I should put a G sub Q everywhere. So G sub Q to be the version over this this Q-to-ROM point. And but in fact, a remark is that it's a special case of a group N scheme that you have over all of ZP principal. Okay, and so in particular, one reason we may want to describe this group scheme is that it's saying that what is a module on GM shared Q to ROM? Well, it's exactly a representation of this group scheme G sub Q, or sorry, group N scheme G sub Q. Well, together with, well, so first of all, it's a module over functions on GM, it's a module over the Laurent polynomial ring, but in the category of G sub Q representation. So we may want to describe this category of G sub Q representations.
So this G sub Q is well, this is a it looks like it's a subfunctor of GM times W hat. Right, so you have to specify X and you have to specify this difference which is in W hat. This is probably a partial answer to Volodya's question, right? It's a partial because here you choose a shear.
Yes, it's after you choose a shearing, it's a sub thing. But it's not clear what will happen if you don't choose. So I'm trying to. Sometimes I believe that the only thing I can do is to write equations. Or it may be inequalities, but not doing something abstract. So here you can write the answer just in terms of equalities in something big. Equations inside something. Ideally, I like to have a description of this when I have a not primitive element vector in the same form. Yes, but of course it's going to be not easy.
Okay, so right, so we have this. So what I wanted to do is to describe this, say something about G sub Q, and okay, so that's so theorem. So theorem is that G sub Q is so G sub Q is the one over the Q line, and the theorem is that it's a Cartesian dual. To the following group scheme, to the group scheme A1, together with the group law such that x plus y, product of x plus y is x plus y plus q minus 2 times x.
So the Cartesian dual is surprisingly simple. Namely, it's just a rescaled version of the multiplicative.
Yes, yeah, thanks. So this is rescaled m by q minus 1.
For instance, it turns out Q doesn't have to be infinitely closed. Did we know this? Huh?
Then it's a monoid scheme.
But you can always impose convertibility conditions. So it's
Okay, so in particular, so this is a version of the result that's proved by Volodya in the one-dimensional formal group law paper. Because in fact, this shared construction, and in fact, this kind of the kernel of this map will be the Cartier dual of a smooth group scheme, a smooth commutative group scheme, which provides, I think, another construction of the decompletion of the formal group in Volodya's paper.
So the question which I was unable to answer, and it was posed in my paper, is whether this very simple group scheme descends to ZP. So it's a priori, it's very simple. It's a very simple group scheme over the formal disk. The formal disk maps to ZP prism, but the corresponding and this represents the ZP prism as a quotient of the formal disk by a rather complicated group law. And the question is whether this group law descends with respect to this group void, and that's there is a way to pose this question so that the answer is yes or no. And the answer is yes. And this is so this was originally proved by, I forgot his name, a person from Northwestern, and maybe also by Jacob Lurie. And you give a more natural, or anyway, a different, maybe a more natural one. So there are ones, but suppose I'm not interested in descent and just want to understand why GQ is the Cartier dual to this. Will the arguments from my paper work here more or less, or is it a different story?
I think so. So maybe let me just make one more remark on
just one. But does your definition of GQ make it obvious that it descends?
Well, right. So I mean, this is
GQ obvious by construction, or maybe by Vadim's talk today. It does descend, and therefore its dual also descends.
Okay. Right. So the other comment is that, so I think in my first talk I mentioned that so this also gives rise to right. So in particular, this sort of Cartier duality lets you describe representations of G sub Q in terms of modules on the Cartier dual, and so in particular, this gives the correspondence or equivalence between quasi-co of GM sheared theorem and this category of Q connections. Everything is P minus 1. Okay, so I could explain this more later if this, but so since there's actually not very much time, let me just say what so this was some motivation. I think this result is not too difficult to prove by some sort of Nakayama's lemma. Essentially, let me give a proof sketch. So proof sketch. Well, the observation.
So what is not so difficult to prove, the theorem or the
theorem?
Theorem.
So let me give a proof sketch. So and this is in fact following studying the for chromal groups. So the proof sketch is based on the observation that so what I called G sub Q, so this group hinge scheme, that this has a natural section. It has a natural section which is given by, let's see, so X equals Q and Y equals, well, whatever it has to be to solve this equation. So I think that's maybe brackets Q minus 1 times brackets Q to the P minus 1. So it has a natural section like this, and it's a section which vanishes when Q equals 1. Okay, so at the level of Cartier duals, that gives you a map from E sub Q dual to GM. So it gives you a map like this. And this map vanishes when q equals 1, because this one vanishes when q equals 1. And then that is exactly what you need to give a map to this rescaled GM. So that gives you a map to this rescaled q minus 1 rescaled GM. And well, then you have to check that that map is an equivalence by some sort of Nakayama's lemma on the special factor. So okay, so that's a proof sketch. But I think so I guess what we don't have time to explain today. But in fact, the point is, maybe it's not so clear exactly what Cartier dual means in this context. So maybe so this G sub q of R, or I'm sorry, this G sub q, it's a group in scheme. Well, we want to say that it's Cartier dual. We want to say that G sub q is Cartier dual to a very nice smooth commutative group scheme, and in particular, it's not, well, maybe it's not a priori clear that G sub q has some sort of flatness. So maybe so this is the proof sketch, but maybe the main point is that G sub q actually satisfies some sort of flatness as an in scheme. So G sub q satisfies a flatness condition as an in scheme that enables one to show that the Cartier dual of G sub q is something that one can define and prove to be a smooth affine group scheme. So a priori, if we just define G sub q via this formula, it's not so clear that doesn't seem clear that it has a well-defined Cartier dual, which is a smooth commutative group scheme.
For instance, we would like to claim that so we can look at the coordinate ring of this in scheme. It's because it's an in scheme, the coordinate ring is topological.
Yes.
And one would like to prove that this topological ring is the linear dual of a projective. This requires some thinking.
Yeah, so that's what we
we're then thinking, and this is what you are not going to explain today.
Which I can continue.
And you will explain this some very general framework which proves this.
So basically, the main thing one has to do to make this proof work is to show that G sub q has a well-defined Cartier dual, which is.
And then one can ask, what is the correct framework for Cartier duality between indefined schemes and commutative affine schemes? This was the question which you posed in your first or maybe second talk, and now you have an answer. And you will explain it next time.
Sure.
But for today, this is
I think it's a good place to start.
And just an organizational question. So do I understand correctly that the next meeting is next month?
Yes.
I have a small question. GQ has very, very simple description. Cartier dual to GQ.
Yes.
Very simple description. But what about the Cartier dual to G itself? So you also want to have a very simple description, right? So it's a smooth affine group scheme over a ZP. So in principle, we want to descend this explicit description of the Cartier dual to GQ to some smooth affine group scheme over ZP. If you explain that how to descend at least to ZP sheared prismatization, to the sheared prismatization of ZP. All you need to do is to explain how ZP cross acts on this group scheme, right? So that you which is this rescaled version of G. So there is an action of ZP cross on the Q-theorem prism, and you have to explain why this group scheme is equivalent with respect to action of ZP cross. Is it possible? So once you do this, you have to check that this action of ZP cross satisfies certain condition. When Q is 1, it's trivial, something like this. Yeah, trivial. Then it descends to, according to the first theorem that you stated in your first lecture. Then it descends to ZP shared, to the shared prismatization of ZP. And then I think you explained that the category of quasi-coherent sheaves on ZP on the prismatization of ZP is a full subcategory of the category of quasi-coherent sheaves on the shared prismatization. In particular, this is true also for groups. The category of groups over ZP prism is a full subcategory. So is it possible to do it? Is the first step. So what I'm saying is that to explain, to construct the descent, well, you need to construct just action of ZP cross, plus you have to verify certain conditions.
Yes, that's right. So it's a property that it descends from
Yes.
ZP shear prism to ZP prism.
And action of ZP cross means that you raise, so you have some alpha in ZP cross, and now if you have such an alpha, you can raise Q by, we can replace Q by Q to the power of alpha. Then you get a new multiplication law. And the claim is that the two multiplication laws are canonically isomorphic. And Vadim is asking whether you can explicitly construct the isomorphism.
I think so. I mean, I think this construction of rescale GM depends on a divisor. So I think well, maybe the formula might be a little bit messy, but
yes, it's you are just saying that it is Q minus 1. The relevant thing, so multiplying by Q minus 1 by a unit obviously doesn't change up to canonical isomorphism. And then the observation is that if alpha is any unit in ZP, then Q to the power of alpha minus 1 divided by Q minus 1 is the unit. Yes, sounds fun. But okay.
So am I right that so you have a map from the Cartesian dual to GM, and then GM, well, it lives inside the formal GM. And in the formal GM, you have action of ZP cross.
yes. But I think you have a ZP cross action on the whole Algebraic thing as well. So
Yeah. I'm just saying that the formula is, well, it's for ZP cross section. Probably it's. I hope it's very simple. You take. Well, the map to GM is given by formula.
Multiplication by the unit.
Yeah.
Multiplication by the quotient. Yeah. Right, so I think, yeah, so in particular you can use it, right? So I think what you're saying, you can use this to also completely describe this group over ZP shared prism, because once you have G sub Q and once you have the ZP cross action, well, satisfying a property, that's enough to completely describe it over ZP shared prism, and then it's a further property, nilpotent property that I guess one can check, that it descends to ZP prism.
Other questions or comments?
I mean, here that a section gives you a map in from the constant group scheme on ZP and then neutralize that.
Other questions? Let us thank the speaker.